Here you see a picture of the Nobel Prize winner and one of the most famous expositors of physics, Richard Feynman. Richard Feynman had a reputation of being able to do the toughest of integrals with ease. Here is a passage from his semi-biographical work, Surely You're Joking, Mr. Feynman. I had learned to do integrals by various methods shown in a book that my high school physics teacher, Mr. Bader, had given me. It showed how to differentiate parameters under the integral sign. It's a certain operation. It turns out that's not taught very much in the universities. They don't emphasize it. But I caught on how to use that method, and I used that one damn tool again and again. If guys at MIT or Princeton had trouble doing a certain integral, then I come along and try differentiating under the integral sign, and often it worked. So I got a great reputation for doing integrals, only because my box of tools was different from everybody else's, and they had tried all their tools on it before giving the problem to me. So this is a very practically useful tool that will allow you to solve difficult integrals. The importance of this tool is nowadays not that much, simply because we have symbolic packages like Wolfram Alpha that can do differentiation, that can do integration. But nevertheless, it's a tool that's good to know. So I'm going to state and prove one version of differentiating under the integral sign. This will turn out to be very useful when you do stuff like complex analysis and you want to prove some integral formulas. You can just differentiate under the integral sign. It will allow you to give very elegant proofs of certain theorems. So without much further ado, the statement of the theorem. The setup is as follows. U subset of Rn is open, and we have f from u times the closed interval ab to r, a continuous function. Okay, and think carefully what this means. Continuity is going to be defined using some metric on the product. Here it's going to be the Euclidean metric at a continuous function. Okay, suppose the partial derivatives of f with respect to the first n variables exist and are continuous on u cross ab. Okay, so this is essentially just saying that the function is differentiable, the function's partial derivatives exist with respect to the variables coming from u. So in some sense, this function is differentiable when treated as a function of u. Okay, so each partial derivative will define a function from u cross ab to r. That function should also be continuous. Now what we are going to do is we are going to define this new function g of x, which is given by integral a to b of f of x t dt. So in essence, g is a function from u to r. So for a fixed x, you fix the variable slot x here in the function f, you get a function of t, f of x t. This function is obviously going to be continuous from the facts we have established when we studied metric spaces. Then just integrate this function with respect to t. That will give you the function g of x. That will give you the value g of x. In this way, you get a function g from u to r. Now, what differentiating under the integral sign says is then g is actually a c1 function on u. It's continuously differentiable. Partial derivatives exist and are continuous. And di, the partial derivatives di of g of x, is nothing but integral a to b di of f of x t dt. Okay, so the partial derivatives exist and are continuous, and the partial derivatives can be obtained by simply shifting the derivative operator di inside the integral sign. Okay, let's prove this. The proof is not hard. Fix x in u. Fix x in u. Okay, now by replacing u with a small ball centered at x, we assume f is bounded on u. Differentiating a function is a local thing. The derivative of a function, the existence and the value of the derivative depends only on the value of the function near that point. So all we are going to do is we replace u by a small ball centered at x, and we assume that f is bounded on u. Okay, now let's just compute and show this result for the first derivative. All the other derivatives follow in the exact same manner. What we are interested in is g of x1 plus h. The rest of the variables I am denoting by x prime. x2 to xn is denoted by x prime, minus gx minus h times integral a to b d1 of f of xt dt. Okay, so I have just considered essentially the linear approximation. I'm just subtracting the linear approximation of g, considered now as a function of just the first slot. All the other slots are fixed. I'm writing down the difference. Now for this function to be differentiable and the derivative to be this quantity, integral a to b d1 of f of xt dt, all we have to show is this whole thing divided by h, limit h going to 0 is 0. If you could show that, we are done. Okay, so that's the aim. So we will just analyze this quantity in some detail and see what happens. Okay, now what I'm going to do is, we know the definition of g, it's in terms of an integral involving f, so we just write this as integral a to b f of x1 plus h, I forgot an x prime, so f of x1 plus h comma x prime comma t now, because there is a t slot, and in fact you are integrating along this t slot, minus f of xt. Okay, and what I'm going to do is I'm going to just bring this derivative, the candidate derivative, also inside f of xt, the whole thing dt, integral from a to b. Okay, so this is just straightforward properties of the integral. By the way, this integral, I didn't speak about that. This integral exists because d1 of f of xt is a continuous function of in fact on u cross u, and we are just fixing this x and treating it as a function of t, and it's certainly going to be continuous when you restrict it and treat it just as a function of t. So this, what is the integrand, is actually continuous, so this integral exists. That needs to be said actually. Now for the next step, I'm going to apply a trick. First, observe that if you have consider the function f of x1 plus uh comma x prime comma t. This I'm going to treat it as a function of u. Okay, I'm going to treat it as a function of u, and this function I'm going to assume that h is chosen so small that this as a function of u is defined from 0, 1 to r. Okay, so we are already taking h quite small. We take h so small that this function treated as a function of u alone and as no other variable is well defined as a function from 0, 1 to r. Okay, we choose h so small that this happens. Okay, now if you differentiate this function, remember it's a function of u, it's a one variable function, you will get, by the chain rule, you will get d1 of f of x1 plus UH comma X prime comma T, and because we applied the chain rule, you will get into H. Okay, this will be the derivative of this function. Consequently, if I integrate this from 0 to 1 du, if I integrate this from 0 to 1 du, the derivative and the integral will just vanish. I will just get f of x1 plus uh comma x prime comma t with the limits 0 and 1, which is just f of x1 plus h comma x prime comma t minus f of x1 plus 0. So that's just f of x1 plus f of x1 comma x prime comma t, right? So putting all this together, this big expression that we have to deal with, I can replace these first two terms by this integral. Okay, so putting all this together, I will just write equal to. So this equal to is technically following on from here. It's following on from here and on to the next page. This equal to integral a to b integral 0 to 1 d1 of f of x1 plus uh comma x prime comma t h du, and this integral closes, minus h d1 of f of x t, and this whole thing is integrated with respect to t. Okay, so this is the net upshot of the observations that I made in the previous end of the previous slide. This is nothing but integral a to b. Now I'm going to bring that second term h d1 fxt also inside, noting that there is no u dependency there. I can write this as integral 0 to 1 d1 of f x1 plus uh comma x prime comma t minus d1 of f of x t, this whole thing h du dt. I can do this because there is no u dependence on the second function, so I can may as well integrate with respect to u. Note that I'm integrating from 0 to 1, so it doesn't really go, it's the same as just writing h d1 fxt. Integral 0 to 1 h d1 fxt du is same as just h d1 fxt. Okay, now we have to estimate the terms. So we are interested in estimating norm of g of fx1 h. So this is not actually a norm, this is just a modulus. We are interested in estimating g of x1 plus h comma x prime minus g of x minus h integral a to b d1 of f of x t dt. Okay, this is certainly going to be less than or equal to maximum value of the modulus of d1 of f of x1 plus uh comma x prime comma t minus d1 of f of x t times the norm of h times the b minus a. Okay, where the maximum is taken over the rectangle a less than or equal to t is less than or equal to b, and 0 is less than or equal to u is less than or equal to 1. This immediately follows from taking the modulus. So we have to essentially take the modulus here to estimate this. So we just move the modulus inside and just apply standard facts about integrals that we are already familiar with, and from that we will get it. So just one error, there is no norm on h, there is just, it's just mod h. This is just mod h, right? Everything is just a real variable. Okay, this is a straightforward step. I'm going to leave the details to you. So now fix epsilon greater than 0. Okay, so by continuity of d1f for each t in AB, for each t in AB, we can find an open interval IT, which is a subset of AB. So open in AB. Okay, open in AB. So that means this openness, it's not an open subset of R, but rather an open subset of 0, 1. Please recall what this means by going through the relevant section in the chapter on metric spaces. And a ball BT subset of U containing X such that the modulus of d1 of f of ys minus d1 of f of xt is less than epsilon for all y in bt and s in it. So I have just applied the definition of continuity at the point xt. I am varying t. For each t I will get an open interval it subset of AB and ball bt that contains x such that this will be true. This is just restating the definition of continuity for the function d1 of f. Okay, here is the key fact. By compactness, finitely many subintervals IT1 to let's say ITK cover this closed interval AB. Okay, now this is a somewhat tricky thing because the open intervals that I'm considering are open in AB, they are not open intervals of R. But recall from the chapter on metric spaces that compactness doesn't really depend on which ambient space you consider. So what I'm saying is perfectly valid. You can check it thoroughly. Please check that to make sure that you understand why this is correct. Let B be the corresponding or rather intersections be the intersection of the corresponding BTs. Okay, or rather BTIs, corresponding BTIs, that is BT1 intersection BT2 dot BTK. So we have covered AB by finitely many open intervals, or rather finitely many open intervals, open in closed AB. I re-emphasize that. Now we are taking the intersection of the corresponding BTIs. So once we take this intersection and apply this compactness argument, what we can conclude is that we get some sort of uniform continuity. What I mean by that is we can conclude that modulus of d1 of f of yt minus d1 of f of xt is less than epsilon for all y coming from the single ball B and t coming from 0, 1. Okay, so by applying this compactness argument, we get some sort of uniform continuity on the derivative d1. What this allows us to do is if we choose h so small that x1 plus h comma x prime is always in P, then we get the norm of g of x1 plus h comma x prime minus g of x minus h integral a to b d1 of f of x t dt. This whole thing, it's not norm, it's just modulus, is less than or equal to epsilon times h times b minus a. Okay, so this just follows from the estimate we just got above, that d1 of f of yt minus d1 of f of xt, the absolute value of that is less than epsilon. Okay, and clearly this proves that d1 of d1 of g, correct, d1 of gx is equal to integral a to b d1 of f of xt dt as claimed. Well, the other partial derivatives can be done in the exact same way. So this was a somewhat tricky proof. It's not hard, it's somewhat tricky because you have to apply this somewhat different type of compactness argument. But essentially you get some sort of uniform continuity that allows us to do this. You can get a better argument for this if you invoke what is known as the dominated convergence theorem. That will allow you to prove this in a much easier way instead of this somewhat tricky argument. This is a course on real analysis, and you have just watched the video on differentiating under the integral sign.